Hello CAPE students, it's class time and we've come to the chemistry segment today and we will be looking at one of life's most fundamental parts, the atom. Specifically, we'll be learning about atomic structure. I'm Ricardo Price and I'll be your teacher for this lesson. Let's get started. For today's presentation, we'll begin with the atom because we're talking about atomic structure today. And then we'll move to Dalton's theory, isotopes and radioisotopes, and then we'll do a few questions. We'll then move to calculation of the relative atomic mass, the Bohr model, and atomic emission spectrum, and then we'll conclude with some questions. Today, we have a general understanding of what atoms look like. We know that it is made up, it makes up everything in matter, solids, liquids, and gases. Initially, in the 1600s and 1700s, scientists couldn't conceptualize atoms being this small, positive particle with a positive nucleus with electrons circulating around it. If they saw a block of cheese, they would say, okay, the cheese is made up of cheese particles, which kind of makes sense. It was not until a scientist, John Dalton, in 1808, that came up with his theory on atomic structure that we gleaned the knowledge that we have on atoms today. Now, Dalton's theory essentially states that matter is made up of atoms, and an atom is the smallest, most indivisible particle known to man, meaning that it cannot be broken down into anything else, right? Further studies on Dalton's theory by Ernest Rutherford, gave us some more insight on atomic structure, and we learned that atoms consist of a small positive nucleus with electrons orbiting this nucleus. How did Ernest Rutherford know this? No, he did an experiment called the gold foil experiment, and he used a radioactive element. Have you ever watched TV and you see a radioactive substance such as uranium, and it glows, right? You see this bright neon green light, and that is uranium giving off radiation. It gives off radiation in the form of waves as well as particles. Now, imagine that this block is uranium, right? And it gives off radiation in the form of alpha particles. Now, alpha particles, we'll touch on that a little more in this presentation, but for now, accept that alpha particles are small, positive particles. Now, this radioactive element is giving off radiation like this, right? And it's enclosed in a lead case. Now, there's a little slit that allows the radiation to escape. Now, there will be a beam of alpha particles exiting this slit, right? And it will come in contact with a thin foil, a golden foil. And you know that gold is an atom. So he wanted to see what would happen when the alpha particles interacted with this gold foil. He wanted to know, would it go right through? Would it be deflected? Or would it bounce back right to the source? He realized that most of the alpha particles passed right through the gold foil and to the detector. A very small amount was deflected at angles, and a smaller amount was deflected right back to the source. Now, what does this mean? This means that the atom is made up mostly of empty space because most of the alpha particles passed right through the gold foil and a small amount bounced back. He concluded that the atom has a small positive center called the nucleus. He said that this center was positive because it repelled the alpha particle, which I mentioned earlier that the alpha particle is a small positive particle, thus the two positive charges repelled each other. So he concluded that the nucleus is small and positive, the atom on a whole is made up of mostly empty space, and it has electrons floating around this positive charge to keep the thing neutral. Now, having the knowledge that we have today on atomic structure, we can see that the atom is made up of a proton, a neutron, as well as an electron. Now, the proton and the neutron virtually has the same mass, 1.67 times 10 to the minus 24 grams. The charge on the proton is 1, while the charge on the neutron is 0, because it's a neutron. Neutral, neutron, okay. So, the relative masses of each, the proton and the neutron, is 1, because they're in a 1-to-1 ratio. The mass of the electron is way smaller than the mass of the proton and the neutron, and it's 9.11 times 10 to the minus 28. The charge on the electron is minus 1, and its relative mass is 0. But why is the relative mass 0? The relative mass is 0 because the mass the electron contributes to the total mass of the atom is negligible, because it's so much smaller than the other two subatomic particles, the proton and the neutron. Now let's take a look at Dalton's theory. Dalton stated that all matter is made up of atoms. Makes sense? He stated that atoms are indivisible and indestructible. He also stated that atoms of the same element are identical in mass and properties, and compounds are made up of 2 or more different types of atoms. And he also stated that a chemical reaction is virtually a rearrangement of atoms. Now, there were some problems with this theory, and I'll highlight the problems. He stated that atoms are indivisible and indestructible. But we know that an atom consists of a proton, a neutron, and an electron. So the atom contains subatomic particles which can be separated from the atom on a whole. So atoms are not indivisible. It can be divided into its subatomic particles. He also stated that atoms of the same element have the same mass. What he means by this is that if you have the carbon in a pencil point versus the carbon in charcoal, they should be the same carbon, because it's carbon. It should have the same mass and it should have the same property. But this is not the case, because we now know that there is such a thing called isotopes. Now, all these elements, as you see here, they're all hydrogen. They have the same proton number or atomic number because they have the same number of protons. But they vary in mass. Why do they vary in mass? They vary in mass because they have a different number of neutrons. The first one, protium, has 1 proton and 0 neutrons. The second one, deuterium, has 1 proton and 1 neutron. The third one, tritium, has 1 proton and 2 neutrons. And it varies in mass because with tritium it has 2 neutrons, 1 proton, so you add those 3 together and the mass would be 3. With deuterium, you add the 2 together, the mass would be 2. With protium, it only has a proton, so the mass is 1. So they're all hydrogen, but they vary in mass. So what is a theory? Looking back at Dalton's theory, one would say that his theory, parts of his theory were disproved, so should his theory be discarded? No, that's not the case. When you look on his theory as a whole, it's a pretty good theory, seeing that he had limited information in 1800. So what can happen is that if certain parts of a theory are disproven, then a new theory, a new revised theory could be put forward. The theory on a whole doesn't have to be discarded. Now, what is a theory? A theory is essentially a group of ideas explaining a certain concept. It can be tested, meaning that I can set up an experiment that can assess the viability of this theory. It should be able to produce reproducible data, meaning that if I carry out the experiment here in Jamaica, somebody else in England should be able to carry out that experiment and we would have comparable data. It should be widely accepted by experts in the field, meaning that academics alike should come together and have a consensus that this theory is scientifically viable. It can be modified based on new data, and that's what happened with Dalton's theory. So although he stated that atoms are indivisible and atoms of the same element have the same must have the same mass, this was not disproven. They just modified the theory and put forward a new modified theory. Now, let's take a look on isotopes and what isotopes are. Isotopes are atoms of the same element with the same number of protons but a different number of neutrons. That is, it has the same mass but a different atomic number. Now, the proton number is the atomic number, and the mass number is the sum of the proton number and the number of neutrons. So carbon has three main isotopes: carbon-12, carbon-13, and carbon-14. Carbon-12 has 6 protons and 6 neutrons. That's why the mass number is 12. Carbon-13 has 6 protons and 7 neutrons, and that's why the mass number is 13. And the same thing for carbon-14, a proton number of 6 and a neutron number of 8. Now, I must say that carbon-12 is the most abundant isotope of carbon, having an abundance of 98.9%. What this means is that if you have 100 grams of carbon in front of you right now, 98.9 grams of that is carbon-12, and 1.1 gram of that would be carbon-13. That's what it means. Now, with these isotopes, the more neutrons you pack into that nucleus, the more unstable the nucleus becomes, and then a concept arises known as radioactivity, and that isotope is termed a radioisotope or a radioactive isotope. Now, what is radioactivity? Radioactivity is the spontaneous breakdown of an unstable nucleus by the emission of alpha and beta particles as well as gamma rays. I'll touch on these forms of radiation further in the presentation. Now, if we should look at this diagram, we would see the parent nucleus, which would be the radioactive isotope, with extra neutrons in there. So the nucleus is very compact, a high energy system, and it needs to relieve some of this energy. So what happens is that it gives off radiation in the form of alpha particles, which I mentioned earlier before. Now, when it gives off this alpha particle in the form of radiation, it then becomes smaller and generates a daughter nucleus. And that daughter nucleus is thus more stable than the parent nucleus because it gave off some of its mass. It's not as compact as before. So this daughter nucleus is a lot more stable than the parent nucleus. And as the slide says, it occurs when there is an excess of neutrons in the nucleus and the more stable atom is formed in the process. Now let's have a look on these forms of radiation. Now, an alpha particle, as I said before, is a small positive particle. It's essentially a helium nucleus. And a helium atom looks like this. A helium atom has 2 protons and 2 neutrons, with 2 electrons orbiting the atom. Now, if we should remove those two electrons, we would end up with just the nucleus, right? And that nucleus would have a 2+ charge. So an alpha particle is basically a helium atom without its electrons, virtually a helium nucleus. A beta particle is virtually an electron, and it has a charge of -1. And gamma rays are high energy rays, high energy radiation, and it bears no charge. So essentially, if we should pass all three of these radioactive particles, if we should have a source, a radioactive source, that emits all three if this is a radioactive source and it emits alpha particles, beta particles, and gamma rays, what we would see is that for the alpha particle, all right, let me put the alpha particle down here. Alpha particle here, beta particle there, gamma particle in the middle. What would happen is that the beta particle would deflect to the positive electrode. This is an electric field. The gamma radiation would pass right through undeflected, and the alpha particle would slowly deflect to the negative electrode. Because the alpha particle is positive, so it would go to the negative electrode. The beta particle is negative, so it would go to the positive electrode, and the gamma particle would pass right through. That's because it's neutral. I should also mention that the beta particle would be deflected at a greater rate because the mass is so small. So it's easy for the positive electrode to pull that beta particle towards itself, while the alpha particle is a lot heavier. So it's not as easy for the electrode to pull it towards itself. And this is just a diagram showing gamma rays being given off. Gamma rays aren't particles, they're just radiation. Now, having a look at these particles, the alpha particle has a mass of 4 and a charge of +2. The beta particle has a charge of -1 because it's an electron, and it has a mass of 0 because the electron's mass is so small. The gamma rays, it's just radiation. So the mass is 0 and the charge is also 0. As you can see on the screen, how we represent an alpha particle is we write helium with the mass at the top and the charge at the bottom. The beta particle is written as with the beta sign. Beta is a Greek letter, as you can see on the screen. The mass of the beta particle is 0, the charge is -1. The gamma particle is neutral, so the charge is 0 and the mass is 0. So, if we were to be exposed to these forms of radiation, how would we stop them? Now, an alpha particle is relatively big compared to the other particles. Now, the alpha particle can be stopped by paper. The beta particle is a lot smaller, so it can penetrate the paper, but it can be stopped by aluminum. The gamma particle is high energy radiation. Thus, it can pass through paper, pass through aluminum, and can only be stopped by thick sheets of lead. Now, for the applications of radioisotopes, let's start with carbon-13. Carbon-13 is used in radiocarbon dating. Now, a simplified view of how it works is that if you have a radioactive nucleus, it needs to give off energy. It needs to lose some of its mass because it has an excess of neutrons, right? So it would give off this mass in the form of alpha particles and beta particles. And at some point in time, it would halve its mass, right? Now, the time it takes for carbon-13 to halve its mass is about 11,400 years. So the geologists studying these artifacts would see that, would dig up these artifacts and realize that, hey, this artifact has a specific mass of carbon-13. Thus, it has a specific mass of carbon-13, thus it would have a certain age, maybe 11,400 years, if they realize that the mass of carbon-13 has been halved. That's a simplistic overview. It's more complicated than that, but that's just the gist of how it works. Iodine-131 is also used to treat thyroid cancer. It has a half-life of about 8 days, so it won't stay in the body too long to cause too much harm. So what the doctors do is that they administer the iodine-131 to the area where the cancer is, which is the thyroid gland in the throat, and the radiation being emitted by that radioisotope kills the cancer cell, and that radioactive isotope will not stay in the body too long to cause too much harm. And everyone knows uranium, uranium-238. It's a good power source. It's used to power nuclear submarines, nuclear power stations, and it's even used to make bombs. Now, let's do some questions. Okay, so the first question states that radiocarbon, or carbon-14, is the radioactive isotope of carbon, and it contains 6 protons and 8 neutrons and has an overall mass of 14. Show the equation for the beta decay of this isotope. Now, what do they mean by beta decay? Beta decay means that carbon-14 has lost a beta particle. So we know that carbon-14 is written like this. The mass number is 14, the atomic number is 6, and we said it lost a beta particle. And a beta particle has a mass of 0 and a charge of -1. And then it goes on to form something, a daughter nucleus, that we don't know what it is. So, since carbon-14 lost this, it would make sense to subtract the values from this, from this. So, 14 minus 0 is still 14. So, this unknown element that is formed has a mass of 14. 6 minus -1, not 6 minus 1, 6 minus -1. This is equivalent to 6 plus 1, which is equivalent to 7. So this unknown element has a mass of 14 and an atomic number of 7. If you should look on your periodic table, you'll see that the element that has an atomic number of 7 is nitrogen. And that's the equation that we have. The next question, uranium-238, which has a proton number of 92, undergoes alpha decay to form what new element? Now, alpha decay means that it lost an alpha particle. So, therefore, the answer would be uranium-238 losing an alpha particle to generate thorium-234. And the atomic number would be 90. Question 3. It says, suppose uranium-238 would undergo gamma decay, meaning that uranium would lose a gamma particle. What do you think would be the product of this reaction? If uranium-238 were to lose a gamma particle, it would still generate uranium-238. It didn't lose any mass and it didn't lose any charge, it just lost energy. So this would be the equation. Now let's jump to calculating relative atomic mass. Now, each atom in nature exists in certain ratios. As I mentioned before, carbon 12, 13, and 14 exists in certain ratios. If you should look, carbon 12 exists in a 98.9% ratio with carbon 13, which exists in a 1.1% ratio. Now, to find the mass contribution of each isotope, what we would do is multiply the mass of the carbon times the abundance of that isotope. So for carbon 12, the abundance, 98.9% written as a decimal, is 0.989%. And then when we do that, we'll get 11.868, and then we do the same for the other isotopes, and then we sum them. So it's the mass of the isotope multiplied by its abundance for each isotope, and then we just add them together. Once we add them, we'd realize that carbon 12 has a mass of about 12.02 grams. Let's try the same thing for chlorine. Chlorine naturally exists as two isotopes, chlorine 35 and chlorine 37. Their relative isotopic abundances are 75% and 25% respectively. Calculate the relative atomic mass of chlorine. Now, to get the relative atomic mass of chlorine, all we do is multiply the masses by the abundance. So, for chlorine 35, we multiply 35 by 75, by 0.75, which is its abundance, and we will get 26.25. Now, for chlorine 37, we multiply 37 by its abundance, 0.25, and we will get 9.25. Once we add those together, we will realize that the mass of chlorine is 35.5. Now, let's move on to the Bohr model. We've come to know that the Bohr model depicts electrons floating around in these orbitals. And if we should look at the Bohr model, we will realize that the electrons are never found in between orbitals. It's always located on the orbitals themselves. Niels Bohr also stated that the energy of the orbitals are quantized, meaning that they have a fixed energy, and each element is unique. Each element has a unique amount of electrons. Now, he also did some experiments where he exposed certain elements to energy in the form of fire, electricity, and he realized that each distinct element burned with a specific color. Now, what actually happens when this element is exposed to energy? Imagine that electron, the lower electron, is in the n equals 2 level, and then the most outer orbital is n equals 3. When the electron is at n equals 2 absorbs energy from the fire, it is excited and elevated to the n equals 3 level. Once it falls back down, it will emit the energy that it absorbed in the form of light. So we see this in fireworks where different elements, example sodium, which burns with an orange flame, boron, which burns with a green flame. This is exhibited in fireworks where these elements are packed into the firework, and once exposed to the flame, they would burn with a distinct color. Now, are you guys aware of how a prism works? A prism works by passing white light through the prism, and the prism separates the white light into its distinctive colors. Now, if we should look on the spectrum generated, it would be a continuum. of colors. So red runs into orange, into yellow, green, and all the way to purple. Now, I mentioned before that these elements, they give off a distinct color when exposed to fire or energy in the form of electricity. And you can see from this diagram that each element, each one of these noble gas gives off a distinct color when electricity is passed through. Now, the idea was that once this element gives off a distinct color or light, that light will be passed through a prism to see what was formed. Instead of obtaining a continuum of colors, we obtain what we call a line spectrum, and this is what drew Niels Bohr into saying that energy is quantized, because there was no attachment of the colors. The colors were separated in the form of lines, and that's what drew Niels Bohr into saying that electrons orbit the nucleus in orbitals. So he came up with the model that we accept today with the nucleus at the center, the orbitals around the nucleus where the electrons orbit. And he said that discrete lines in the spectrum show that energy levels are quantized, which I just mentioned a while ago. An exact amount of energy is required for there to be electronic transition, meaning that if this is the atom and this is n equals 1 and this is n equals 2, imagine that the difference in energy here is 100 joules. If you should provide this electron with 50 joules, it would not go halfway and come back. It would not move. If you supply it with 99 joules, it would not move. If you supply it with 101 joules, the electron would not move. You have to supply it with exactly 100 joules for this electron to move to that orbital and fall back. So, let's attempt some questions. All right, the first question says, determine the energy of light, 540 nanometers, given off when an electron in n equals 2 energy level transitions down to the n equal 1. And we should use the equation E is equal to hc over lambda to guide us, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. Now first we have to convert the nanometers to meter by multiplying the nanometer value by 10 to the minus 9, and then we will obtain 5.4 times 10 to the minus 7 meters. Once we get the meter value, we can plug this into the equation. Planck's constant is given in the question, 6.626 times 10 to the minus 34 joule second multiplied by 3 times 10 to the 8 meters per second, which is the value for the speed of light. And all of this is divided by the wavelength that we just obtained. The answer would be 3.68 times 10 to the minus 19 joules. All right, let's attempt another question. Question 2. It says, calculate the wavelength of light which has a frequency of 2.4 times 10 to the 15 hertz. Now hertz is the same as per second, given off from an electronic transition from the n equals 5 energy level to the n equals 1. So that's a big jump. All right. So for this equation, we'll use the equation nu is equal to c over lambda, where nu, which is basically a v, is equal to c over lambda, where c is the speed of light, lambda is the wavelength. In this question, we want to calculate the wavelength, so we have to transpose the formula to find the wavelength. And lambda is now equal to c over the frequency. Once we plug in those values, we divide the speed of light 3 times 10 to the 8 meters per second by the frequency, which is given in the question, and we obtain 1.25 times 10 to the minus 7 meters as the wavelength. When we convert this value to a nanometer value to see where on the electromagnetic spectrum it would fall, we realize that the wavelength value in nanometers is 125 nanometers. And we get this by just dividing the meter value by 10 to the minus 9. And we get 125 nanometers. Now, we see with our eyes a very small part of the electromagnetic spectrum. Now, looking at this diagram, we only see from about 380 to 750 nanometers. Our value, which was 125, falls in the UV region of the spectrum. Thus, we are unable to see that color. So if you should get a value that is about 550 nanometers, you'd see maybe an orangish, yellowish color. But our value was 125 nanometers, meaning that it falls in the UV region of the spectrum and we can't see it with our naked eyes. Now, for the next class, we will cover periodic trends, where we'll do the orbitals, ionization energies, and as well as forces of attraction, which is basically ionic, covalent bonding, hydrogen bonding, and metallic bonding. So, all right. So hopefully you guys can prepare for what we have next time, and that will be know the shapes of the orbitals, ensure that you cover ionic, covalent bonding, and ensure that you recap the lesson that we just covered today about atomic structure. Ensure that you recap the atomic structure. So today we covered isotopes, we covered Dalton's theory, we did a few questions, we calculated the relative atomic mass, we went through the Bohr model, we went through atomic emission spectrum and how orbitals and energy levels are quantized, and we also did some questions on that, and I hope that this was helpful for you guys. That's it for today. I hope the lesson was clear. However, if you have any questions, send them to Television Jamaica's Facebook page or Instagram at television_Jamaica, or use the hashtag TVJClassTime. And make sure to join us again tomorrow for more CSEC and CAPE classes. Until then, stay curious and stay safe.